Okay, so we are working on problem number 8 here. The first thing I want to do anytime I do a problem on an incline is draw my force body diagram. And I know the force body diagram when it's on a flat surface pretty well, so I'm going to focus on the force body diagram when it's on the ramp. I've got mg down and a normal force perpendicular to the surface. Now when I'm working with a rotated with an inclined plane, I rotate the axis so that I can see the components a little bit better. So here's my force normal, here's my mg, and then my component of mg opposing the normal force is mg cos theta, and this one is mg sine theta. So in this scenario, I have rotated my angled ramp to now be the positive x direction. Okay, so in this scenario, I'm solving for the velocity of the cube as it leaves the inclined plane. So I'm going to start with a LOL chart, knowing that it has velocity, so that's kinetic energy in the beginning. And then it starts moving up the ramp, and it has some kinetic energy, and then it's got some gravitational energy as well. So UG. Okay, so in this scenario, what I want to do is figure out what my kinetic energy is. That's going to be the 1/2 mv squared. And I have that velocity value, but I also know that as it travels up the ramp, some work is going to be done to it by this component of gravity. So I'm going to subtract the work done by that component, which is force times distance. The force is mg sine of theta, and the distance is my value for the length. Now, once it hits the end of this ramp, it's going to launch out at a specific velocity. And that velocity is going to be going in my positive x direction here. I should use a different color. So my velocity is going to launch out in this x direction. So don't think of that red line as part of the force body diagram. I just wanted to show you that because we've called this the x-axis now, we're going to ignore the gravitational energy and just try to find this velocity moving in our defined x direction. So we're going to set this whole thing equal to a kinetic energy, 1/2 mv final squared, which is the final velocity we're solving for. The nice thing about this is my masses cancel out if I divide m from all of the components, all the parts of my equation. I end up with v squared over 2 minus g sine theta times L. Actually, I'd rather put the L in the front, so I'm going to call this LG sine theta. I'm going to multiply the 1/2 by 2 on both sides. And then I am going to take the square root to get rid of that squared value. And that's going to give me my velocity. If I plug in all of my values, you should get the answer of, let me pull it up, 6.98 meters per second. Okay, so the next part of this problem, part B, is to find the distance from the base of the inclined plane where the cube hits the floor. So what we have is a velocity of 6.98 being launched at an angle. So I'm just going to draw it here, 6.98, because I'm going to want to break that down into its components. And the angle here is still going to be 37 degrees. So it's going to be 6.98 sine of theta and 6.98 cosine of theta for my x and y component of velocity. Now, I always, when I'm solving for the distance, my range, I always try to solve for the time in the y direction first. I need to figure out what this height value is right here to get my y initial. And that is going to be opposite over hypotenuse. So if this distance here is L, it'll be sine of theta. So my y naught is 2 sine of 37 degrees, which gives me 1.2. My final position is 0 because I want it to land on the floor. My acceleration is negative 9.8. And my initial velocity is going to be 6, I should calculate that, 6.98 sine of 37, which is 4.2. So this is 4.2 meters per second. Let me erase this. Let me erase this here and put 4.2. Okay, so I'm going to have to use a quadratic equation for this, unfortunately. I am going to start off with y is equal to 0. This is the second kinematic equation, is equal to y naught plus v initial times t plus 1/2 at, so that's negative 1/2 9.8 t squared. So I'm going to rewrite this because I like my a's in front. 0 is equal to negative 4.9 t squared plus 4.2 t plus 1.2. You're going to use your quadratic equation. So t is equal to negative 4.2 plus or minus the square root of 4.2 squared minus 4 times a times c all over 2 times a. I end up with a time equal to 1.08 seconds. And then in order to get my range, I need to use x equals x naught plus v naught t. And that initial velocity is just 0. I know my v naught t is 6.98 cos 37. So that's going to be 5.5. This is 5.57, or let's call it 5.6 times the time. And I get 6.02 as my distance. Part C is more just analyzing what would happen if friction were present, so no real calculation, should be easy to figure out on your own, and good luck on these problems.